All right, guys, before we get started, are there questions on any of the assignments so far? Questions on the homework assignments?
Well, actually, never mind. I'll do 11. It's this. Are you kidding?
Would you already do it?
Yeah. I did that in the paper.
So you did get those right. All right, guys, so what we're doing is 2.5. Zero is a polynomial functions. This is the last thing we're going to cover before spring break. So fundamental theorem of algebra, rational zeros, complex, or finding conjugate pairs, finding zeros. Solutions. Fundamental theorem of algebra. So most important thing we get from the fundamental theorem of algebra, if f of x is a polynomial function of degree n, where n is greater than 0, then it has at least one 0 in the complex number system. Even if we say 3 plus 0i, that's a number or solution in the complex number system. Linear factors. If a polynomial of degree n, where n is greater than 0, has it precisely n linear factors, where n is the degree, where C1, C2 could be complex numbers. Now, for the most part, the fundamental theorem of algebra and the linear factors theorem tell you that you can only tell you the zero factors exist, not how to find them. And really with any of these here, it tells us the solutions. So the degree is equal to the number of solutions. And we do have to count repeated solutions. So if we look at this here, the first degree polynomial function f of x equals x minus 2. X to the first power, so the degree is 1. Telling us that it has exactly 1, 0. And this here, we just have to set equal to 0 and solve, and we find out that the one solution is 2. Now with f of x equals x squared minus 6x plus 9, the degree is 2, so we should have 2 solutions. We factor this to here. And we find out that it has exactly 2 solutions, 3 and 3. It is a repeated 0 because it does show up twice as an even multiplicity. And if we look at this third degree, there should be 3 solutions. We can factor out the greatest common factor of x, get x times 2i times negative 2i. Set both of these equal to 0 and solve. So we do have exactly 3 solutions. 2 are in the complex plane, 2i, negative 2i, and one of them is 0. Rational zeros. The rational zeros test relates the possible rational zeros of a polynomial function to the leading coefficient in the constant term. So we take all the factors of the leading coefficient, the number in front of the variable at the biggest exponent, and divide it by all the factors of the coefficient, the number without a variable. And that will tell us the rational zeros. That's pretty much what that just says. So if we look at the rational zeros for this here, let's start with our leading coefficient, Q, and our constant term, P. So Q, the factors of the leading coefficient, would be the number in front of the variable with the biggest exponent. Well, the number in front of the variable with the biggest exponent is 1. The only factors of 1 are 1. Our constant term is 6. So we're looking at the factors of 6. Well, for us, that's going to be 1 and 6 or 2 and 3. Now to find the rational zeros, we're looking at plus or minus P over Q. So we're going to divide every factor of P by every factor of Q. Now here I find it's always good to start with the first value of Q, which is just 1. Well, 1 divided by 1 is 1. 2 divided by 1 is 2. 3 divided by 1 is 3. And lastly, 6 divided by 1 is. So all the rational zeros, all the possible rational zeros that this function can have is plus or minus 1, plus or minus 2, plus or minus 3, or plus or minus 6. So if it does have a rational solution, it has to be one of these 8 here. Questions on this so far? Now, the mathematical way to go about finding these solutions or possible solutions that we can have is taking each one of these. So we can start with 1 and using our synthetic division to solve. Because if 1 is a actual 0 for this here, the remainder should be what? 0. So we can go through synthetic division because we do 1 times 1, which is 1. Then we add straight down. Negative 1 plus 1 is 0. 1 times 0 is 1 plus 0 is 1. 1 times 1 gives us negative 3 plus 1 is negative 2. 1 times negative 2 is negative 2, and negative 2 plus 6 is, so is 1 a solution? No, because it gave us a remainder of negative 8. So, since 1 didn't work, we can move to negative 1 and do this again. Negative 1 times 1 is negative 1. Negative 1 plus negative 1 is negative 2. Negative 1 times negative 2 is 2. 1 plus 2 is 3. Negative 1 times 3 is negative 3. 3 plus negative 3 is negative 6. Negative 1 times negative 6 is 6. So yes, negative 1 is a solution. Now, it could be it again. But if one of them doesn't work at one step, it's not going to work in any other. Because since we said that positive 1 didn't work on the first one, it's not going to work on any of the following. If it's a solution at one part, it's going to be a solution at all of them. Now, we could try negative 1 again and see if this works. Negative 1 times 1 is negative 1. Negative 2 plus negative 1 is negative 3. Negative 1 times negative 3 is 3. 3 plus 3 is. Negative 1 times 6 is giving us negative 12. So that tells us negative 1 did work once. It's just not going to work twice. Because the one solution of negative 1 at this point has been removed. So we can move on from there and try 2. 2 times 1 is negative 2 plus 2 is 0. 2 times 0 is 0. Yep. 0 plus 3 is 3. 2 times 3 is negative 6 plus 6 is 0. And we can keep doing this until we've tried all the solutions, or at least until we get it down to a quadratic, because each time we divide by synthetic division, we decrease the degree by 1. Because when we started this, we started off with x to the 4th. We did our 1 division and reduced it from x to the 4th to x to the 3rd. We did it again, and what we have now is x squared plus 0x plus 3. X squared plus 3 is equal to 0. And the reason we're stopping here is we could have continued on with -2, 3, -3, 6, -6, but none of those are going to work. However, we can solve this quadratic equation. Now, different ways we can solve it. We can do completing the square quadratic formula, factoring, or the square root method. Now, the square root method will work well here because we can subtract 3 from both sides, telling us x squared is equal to -3. At this point here, we'll take the square root of both sides, telling us x is equal to plus or minus. Well, the negative will come out as I, and the square root of 3 doesn't reduce, telling us that the last two solutions are plus or minus I square roots of 3. So these here are our 4 solutions. So none of this is really new. This is, again, we've covered all this before. It's just been a while. Questions on what we've done here? Also, we could have found these 2 solutions by graphing. All right. Let me borrow this. Because if we took the graphing calculator, hit y equals, clear those out, x to the 4th minus x cubed plus x squared minus 3x minus 6. We do see that it crosses the x-axis twice, one at -1 and one at 2. So it does tell us 2 of the solutions. And whenever we're solving, especially if we graph, the number of solutions we want to find at minimum is 2 less than the degree. Or, well, we want to get the degree down to 2. So however many solutions it's going to take to get it from 4 to 2, well, that would be 2. So we need at least 2. So here, -1 and 2 are the only ones that work, getting us down to this here. So those are the factors. And we took it a step further because, well, we found out what's going to make this be 0. So we actually did find all the solutions. Yep. Synthetic division can test possible rational zeros. Conjugate pairs. Now, according to the complex zeros, if there's a complex zero, is a solution a plus bi. It's only a solution if a minus bi is also. They come in pairs, conjugate pairs. If one is a solution, the other has to be a solution as well. For instance, the result applies to the function x squared plus 1, but not to the function x minus I, because that's just 1. So if 3i is a solution, the -3i is a solution. If we have 1, we have to have the other. So find a 4th degree polynomial with real coefficients, -1, 1, -1, and 3. So what that's telling us is, well, it doesn't say it there, is that x is equal to -1, x is equal to -1, and x is equal to 3i. So we do have that. That's what they told us. But from what we know about complex conjugates, or even irrational conjugates. If I have one, I have to have the other. If we have positive 3i, I have to have negative 3i. If I have a positive square root, I have to have the negative square root. If we have one, we have to have the other. They always come in pairs. And really, to find the linear equation, all we've got to do is get all three, or well, four of these here back equal to 0. We're going to move everything back to the other side. So for our x equals -1, well, we're going to add 1 to both sides, giving us x plus 1 equals 0. For our x equals 3i, here we would subtract 3i, telling us x minus 3i is going to be one of our factors. And lastly, x is equal to -3i, we would add 3i, telling us x plus 3i. So we have x minus 3i, x plus 3i, or that the function of set of linear factors is going to be x plus 1 times x plus 1 times x minus 3i times x plus 3i. Is it factored out? Questions on this here? Now, if we wanted to, we can actually find out what this polynomial equation is, of least degree anyways. There we go. Now, to find the polynomial of least degree, we just got to multiply these back out. We just need to multiply them back together to see what the equation is. Now, for this here, whenever we have complex conjugates or conjugate pairs, make sure to multiply them together first before multiplying them with anything else. So we can do the x plus 1 times x plus 1. X times x would give us x squared. X times 1 is going to give us x. 1 times x is going to give us x, and 1 times 1 is going to give us 1. So that's the first multiplication there. We can also do our x minus 3i times x plus 3i. X times x is going to give us x squared. X times 3i is going to be positive 3xi. Negative 3i times x is going to be negative 3xi. And lastly, negative 3i times 3i is going to be negative 9i squared. Now at this point here, we'll combine like terms. We'd have x squared plus 2x plus 1. Here, x squared is the only like term, so we have x squared. Our 3xi minus 3xi would be 0. And lastly, we have our negative 9i squared. Well, as we said before, I squared is -1. So really what we have is negative 9 times -1. Well, the negative and negative would make a positive. So positive 9. And most of the time when I see this I squared, I will cross it out and make whatever number in front of it sign change. We just have to be careful if it's just I squared, because it's turning it to positive 1 or negative 1, depending on the sign in front of it. And lastly, we just got to multiply this out. X squared times x squared is x to the 4th. X squared times 9 is plus 9x squared. 2x times x squared is plus 2x cubed. 2x times 9 is plus 18x. 1 times x squared is plus x squared. And 1 times 9 is 9. And if we combine like terms, x to the 4th is, like terms with it. X cubed doesn't have any like terms. X squared does have like terms. X doesn't and 9 doesn't. So our polynomial of least degree and leading coefficient of 1 would be x to the fourth plus 2x cubed plus 10x squared plus 18x plus 9. Multiply, we get these here. And if we multiply them all together, we get this here of least degree and leading coefficient of 1. So it's just multiplying it all back out. Now, the reason we say least degree is because, well, I'm saying that x minus 1 does not show up more times than what's given. Least number of times with it. And leading coefficient of 1. All right, guys, let's focus in. The number in front of x to the fourth is going to be 1. Because, I mean, we could write it as multiplying everything by 2, 3, 7, 9, 9 tenths. I mean, we can do whatever we want. We just want the simplest version of it. Questions on any of those here? The linear factorization theorem shows that you can write any nth degree as a product of n linear factors. And it includes complex numbers. So every polynomial of degree n greater than 0 with real coefficients can be written as a product of linear factors. Giving that where some of the quadratic factors have no real zeros, which we've kind of gone over so far. The fact that x squared plus 1 is x minus I times x plus I. It's almost we have to solve it, find the complex solutions, and then get them back. Same with x squared minus 2. We solve it, find out that x is equal to plus or minus the square root of 2, set them as two separate expressions, and move them back over. So, we want to find all the zeros of this here, given that 1 plus 3i is a 0 of f. Well, we know that there should be how many solutions? 4. They told us one of them. 1 plus 3i. We actually know another one. 1 minus 3i. Both of these are going to be solutions, or zeros of this here. Now, there's different ways we can go about this here. One of them is that we see what quadratic equation is the solutions for these here, and we can use long division or synthetic division to find it. Find what's remaining or what's left. Now, one of the interesting things with this is that synthetic division, as we saw, does work with radicals, because we saw that we did that the other day. It also works with I. Now, the one that we did in class it kept giving us a remainder, and that's because the value I was using was not an actual solution. But if we use, say, 1 plus 3i, 1, negative 3, 6, 2, negative 60. And again, when using I in the radicals, I would give myself more space than I think is needed, because it's going to get a little bit bigger. We can still do this here. So the first thing we're going to do is multiply. Again, 1 plus 3i times 1. As well as going to be 1 plus 3i. We add straight down, so we add our real and imaginary terms. So negative 3 plus 1 would be negative 2 plus our 3i. Because there is no complex term, so the 3i is just going to come down. Now we're going to have to multiply again. We're going to have to do 1 plus 3i times our negative 2 plus 3i. Well, luckily enough, the graphing calculator, not yet, 3i, will actually let us multiply 1 plus 3i, negative 2 plus 3. It will do it for us, giving us negative 11 minus 3i. Then we need to add straight down. We're going to add 6 to it, which will give us negative 5 minus 3i. Here we can add 6. And we're going to multiply again. So 1 plus 3i times negative 5 plus 3i, which is negative 14 minus 12i. Add 2. So the 2 and negative 14 would give us negative 12 minus 12i. And again, we said this was a solution. So somehow we're going to get a value of 60. Yes. And 2. Then we have our 1 plus 3. I. Yep. And negative 12 minus 12i. Make sure I did that. Negative 12 minus 12i should give us, make sure I did that right. Negative 5 minus 3, yep. Ah. Plus 3i, so we got there. Yep, that's why. So I figured out what happened. I switched the sign. So instead of having, because it should have been negative 5 minus 3i, I did plus 3i, which changes just this, these two. Almost had it. So it should have been our 1 plus 3i times negative 5 minus 3i, 4 minus 18i. Which when we add, we give us 6 minus 18i, and that should fix it. Because now our 1 plus 3i times 4 minus...
Is it 4 or 6?
Let's make sure. Don't want to do that again. 6. Thank you. 6 minus 18i, yes, is 60. And our negative 60 plus 60 does give us 0. So that was one of our solutions. Now, we're going to have to do the same thing with its conjugate pair. 1 minus 3i. Now, 1 minus 3i times 1 is going to be 1 minus 3i. Now, this time we do have I terms, but if we add straight down, negative 2 plus 1 is negative 1. 3i minus 3i is 0. So we just get negative 1. Our 1 minus 3i times 1 is going to be negative 1 plus 3i, because we distribute the negative 1. Negative 5 plus negative 1 would be negative 6. Negative 3i plus 3i is 0. It cancels out. Now 1 minus 3i times negative 6 is going to be negative 6 plus 18i. And if we add those two together, we do indeed get 0. Now what we're left with is a quadratic equation. And if we fill the variables back in, we're saying that we have x squared minus x minus 6 is equal to 0. At this point here, we could factor. Since the 6 is negative, our third term is negative, our signs are opposite. Only factors of x squared are x and x. Factors of 6 are 1 and 6 or 2 and 3. And the factors that we want would have been x plus 2 times x minus 3. Now, since we do have two things multiplied together to equal 0, one of them is going to be 0. Either x plus 2 is 0, which is telling us the value of x is negative 2, or x minus 3 which telling us our value of x is 3. So the solutions are -2 or 3, which really means we could have graphed the function from the beginning and found those two solutions. And because of our complex conjugates, we know that the other two are as well. Factors. So here, they multiplied them together to give us x squared minus 2x plus 10. Then they divided and found the remaining solutions. Picard's rule of sign is another way that we can find possible positive, negative zeros, possible positive zeros, possible negative zeros, and complex zeros. But we're not going to worry about it. Let's see here. One, three. Do not do 83 or 84. Don't do 83 or 84.